This is another video of chapter 9, and at the end of it, the student will be able to define the action potential, name the different phases of action potential, and finally describe the movement of ions during the action potential. First, let's discover what happens if we stimulate a nerve fiber at rest with two different intensities of electric stimulation. We use a voltmeter having two microelectrodes. If we keep the two microelectrodes outside, the voltmeter records 0. But if we introduce one of them into the nerve fiber, the voltmeter records -70 millivolt, which means that the nerve fiber is at rest. Now, what happens if we stimulate the nerve fiber with a given intensity of stimulation? What's happening with this nerve fiber? The membrane potential increases from -70 millivolt to -60 millivolt, then returns rapidly to resting potential. The intensity that triggers this little variation of potential is qualified as non-effective stimulation. And the criterion to consider stimulations as non-effective will be studied later. Now, let's stimulate the nerve fiber with a higher intensity of stimulation. What happens in this case? The membrane potential increases from -70 to +30 millivolt, then decreases to -80 millivolt, then returns to resting potential -70 millivolt. The stimulation that triggers such variation is considered as effective. This variation of potential is called action potential or AP. In fact, we divide this variation of membrane potential into three phases. Let's identify them. In this experiment, we use an oscilloscope to record the action potential. But pay attention. We record what happens at the level of the recording microelectrode and not at the level of the site of stimulation. As you see in the first step, the nerve fiber is at rest and the oscilloscope records -70 millivolt. Look at the polarity of the membrane. The extracellular medium is positively charged and the intracellular medium is negatively charged. Okay, now in the second step, we apply an effective stimulation. So what happens? This effective stimulation triggers a depolarization followed by an inversion of the polarity of the membrane at the level of the site of stimulation. In the third step, the depolarization is able to displace, and when it reaches the recording electrode, the oscilloscope records a depolarization that corresponds to an increase of membrane potential from -70 to +30 millivolt, and this depolarization ends by an inversion of the polarity of the membrane. And look at this region of the neuron. The intracellular medium becomes positively charged and the extracellular medium becomes negatively charged. Now, in the fourth step, the depolarization moves away. It's here now. Okay? And the zone of the neuron at the level of the recording electrode undergoes the second phase of action potential called repolarization. Repolarization is characterized by the decrease of membrane potential from +30 to -70 millivolt. And at the end of this phase, the polarity returns to the initial state, which is positive outside and negative inside. In the fifth step, the same region, this region, undergoes the third phase of AP called hyperpolarization, during which the membrane potential decreases from -70 to -80 millivolt, and after this phase, the resting state is restored. Now, the phases of action potentials are induced by ionic movements between extra and intracellular media, and let's see this video. This is the membrane, extracellular medium, intracellular medium. Okay, we repeat the video for a second time. During depolarization, the Na plus ionic channel is open and the K plus ionic channel is closed. Na plus, which is a positively charged ion, enters the cell, so the potential starts increasing. When the positive charge inside the cell becomes more than the negative charge, the polarity inverts. Now, during repolarization, the Na plus ionic channel closes and the K plus ionic channel opens. K plus, which is a positively charged ion, leaves the cell, so the potential starts decreasing. When the negative charge inside the cell becomes more than the positive charge, the polarity returns to its initial state. Now, during hyperpolarization, K plus ion continues to leave the cell, so the intracellular medium becomes more and more negative and the potential decreases more. After that, the ionic pump intervenes and restores the ionic concentrations of Na plus and K plus ions that characterize the resting state.